Okay, so now we're recording. So welcome to lecture 6. I'll talk a little bit about what we do today. I'll admit I was a little disappointed because I had put that post on Teams to try and garner some discussion on what we were going to cover today, and I didn't get any responses. What I did is I went off of the discussion we had in class last week, and I'll show you what I did. So this was our preference poll, and the orange topics are the ones that we have already done. So we've finished deformables, and then we finished dynamics. And so the question was whether or not we were going to do surveying or geomatics this week or something else. And what I decided was there was a comment, I believe it was from Farah, that said that she'd prefer to do the topics that have that are the bigger topics on the exam, the ones that have the most questions. And that was a good point. And so I looked at the results from surveying and statics, and they were largely similar. I mean, there really wasn't all that much difference. But statics is a bigger section on the exam. And so if we're going to use our time wisely, I'm going to listen to that, and we're going to do statics today. We can circle back and do geomatics or statics, later on, and we can talk about that later. But yeah, I sort of made an executive decision, and today we're going to do statics. And I think that statics is a pretty important concept to cover because statics affects a lot of other things. It affects geotech, it affects fluids, it affects structures. So, you kind of need to know this stuff. If you don't understand centroids and forces and moments and all that stuff, then it's going to make some of the other sections on the exam a lot more challenging. And so what I did is I went through the topic listing on statics. And so the topics are resultants of force systems, equivalent force systems, and rigid bodies. I'll admit I don't know that I technically have a question on equivalent force systems, but I mean all that is just taking a bunch of forces and resolving them into like a force or a moment. The one thing that I'm not covering here is topic D. Well, the two things I should say is topic D and topic F. So topic D is on frames and trusses, and I'm not to cover that because if we choose to do structural engineering down the line, that would probably be a 2-week topic, and we'd cover trusses and shear and moment diagrams and all that stuff in there, so I don't really see a need to do it twice. And as for moments of inertia, I think that if you understand centroids, moments of inertia is just a little bit more added to the algorithm. So I'd rather just focus on developing that base algorithm, and then we can talk about that later. So we have four problems today. One on resultants, one on rigid bodies, one on centroids, and one on friction. And I think that covers a wide swath of what you need to know in statics. And if you don't understand the principles in these problems, then I think it'll make for a difficult exam moving forward. So I think these are some pretty good exercises to assess your understanding of things to come. Excuse me. Okay, so let's jump right into it. And I want to show you the 4 problems, and then we'll break out the notebook. So the first problem is we have the magnitude of the resultant of these forces. I can pretty much tell, this is a very common problem on the exam. This is very popular to do a problem like this. To just be given a series of forces all meeting through a common point, and what is the resultant? Or, another way of looking at it is if it's not this, another spin of this problem is, let's say you've got 4 forces or 5 forces or whatever. What is the magnitude, or what does force 4 need to be such that the resultant is 20 pounds or whatever? So those are very, very common problems. The second problem is just looking at it's sort of a moment problem, and so I guess you can say this is an equilibrium of a rigid body problem because we have to assume or determine what is the tension in the cable that will keep the sign in equilibrium. The next problem is a friction problem. Oh, I thought I clicked over. And so friction, I'm not sure where you're at on friction or how much time you spend on friction in statics, but I think this is a very common problem, is to deal with normal forces and friction. Pretty representative. And other representative problem is a centroid. This is very typical on the exam. It's just to be given some composite shape of triangles and circles and holes and rectangles and all this stuff, and what is the centroid of that area. Very, very common. So let's go ahead and just handle these one at a time. Let's share the screen. Okay, so this is our first problem. And so what we need to do is determine the resultant, the magnitude of the resultant of these forces on the eyeball. So this is a very typical problem that you'll be dealing with in statics, and like I'm teaching it right now, so I'm acutely aware of a lot of this. So the idea is you've been giving a series of forces that all meet through a common point. How can I take these forces and idealize them as a single load? And so the easiest way of doing that is to say that the resultant is the sum of all the x forces and the sum of all the y forces. And you can write this in IJ notation if you want. For problems like this on the exam, you don't necessarily need to write IJK. Probably what I'll do is just separate this into just x and y components, and then just recognize that the magnitude of the resultant is, I take the sum of the x components squared plus the sum of the y components squared, and then just, break out the Pythagorean theorem to handle that. And so that's how we're gonna assess this problem. Now, what I'm going to do is I'm going to number these sources just so that we have something to talk about. So 1, 2, 3, and 4. And so maybe I'll scroll down a little bit. And what I'll do is, you can do this however you want, but what I'm going to do is set up like a little table. And so we'll say force. And so we'll say 1, 2, 3, 4. And then we'll say, how about the x component? And then the y component. Now, if there's really two, in my opinion, there's really two places where you can make mistakes. The first is ensuring that you get your signs correct. So for instance, like if you take force 3, the x component better be positive and the y component better be negative. So that's, because it's going down on the y-axis, and then for force 4, they both better be negative. So, that's probably the first place that you can make a mistake. The second place you can make a mistake comes with your angles, but we'll handle that as we get a little bit more involved with the problem. So let's take each of these one at a time. Let's start off with force number 1. Force number 1 is acting upwards, so it has no component in the x direction. And as for the component in the y direction, it's just going to be 10. And I'm going to put pounds here and pounds here, just so that, we're not having to rewrite the pound symbol all over and over again. Okay, and that 10 pounds is positive because it goes upwards. Okay, now the second force, F2, if we look at F2 is at a 3, 4, 5 triangle. And so you should remember this. I mean, I know most of you have had me for structural analysis, so you should know that I can take this and split it up into its x and y components by saying 3/5 of 15 and 4/5 of 15. And so 3/5 of 15, that is 9, and this is 12. Okay, and so that's pretty easy. For force 3, so we have a triangle like this. That's probably at a horrible scale. Let me see if I can do a little better. That's probably a little better. Okay, and so this is 20 pounds, and this is 30 degrees, and so we need Fy and Fx. And so Fx and Fy, I mean, this is just trig, right? Now, here's where the trip up comes, and so bear with me on this. So in trig, I mean, one of the most foundational relationships that you establish is that the x is associated with the cosine and the y is associated with the sine. And that's fine for force 3. We can do that. We can say 20 cosine 30 and 20 sine 30 here. There's nothing wrong with that. Okay, but there's a reason why there's nothing wrong with that, and I'll explain that here in a second. I'm going to scooch this over a bit. Plus 20 cosine 30, and then 20 sine 30. Okay. Now the sine of 30. This is something you all should be able to handle. So for the y component, that's going to be negative 10. For the x component, that's going to be positive, and it's like 17.32. Okay, so that should be straightforward. Now, here's where things get trippy is on force number 4. Okay, force number 4 is, here's the force. Okay, and the angle that we're given is this one, which is 15 degrees. Okay, and we want to find fx and fy. Now, if you say that this is what 15 cosine 15 and 15 sine of 15, if you do that, that's going to be wrong. Okay, the reason why it's wrong is because your trig functions are associated, x is associated with the cosine, y is associated with the sine. That only works when the angle is measured from the x-axis. This 15 degrees is measured from the y-axis. So there's two ways to handle that. You can either do a switcheroo and put the sine over here and the cosine over here, or you can, instead of using 15 degrees, here's your coordinate system. Instead of using 15 degrees, you can use the 75 degrees here. Either one works, but you just need to be cautious that you're using the correct angle. Okay, so I'm going to use the 75. I don't think it really matters. So minus 15 cosine 75, and then I'm scooching those over so I got room. Okay, and so when you plug and chug, you should get minus 3.88 and then negative 14.49. Okay, and so if I sum these up, and so on the x-axis, or on the x component, so it's 0 plus 9 plus 17.32 plus or minus 3.88, I should say. I get positive 22.44, and on the y component, I get 10. That's positive. So 10 plus 12 minus 10 minus 14.49, I get minus 2.49. So that tells me that the resultant is in the fourth quadrant because it's positive x and negative y. And then if I want to determine the magnitude of that resultant, I would say square root of 22.44 pounds squared plus minus 2.49 pounds squared. Just to make sure everybody's awake, what are we getting for our magnitude of our resultant? $22.58 pounds. There we go. So we can say 22.6 pounds just for rounding. And our answer is D. Oh, sorry, I didn't mean to do that. Okay, before I move on, I want to see if there's any questions on this. I did just kind of like steamroll through it a little bit. because I want to make sure that we're making adequate use of our time. But I also don't think that this problem is incredibly challenging. There are, again, a couple things to get tripped up on. To me, again, the two biggest things to watch out for is ensuring that you write the appropriate signs, you know, that which components are positive and which components are negative, and that when you break out the trig, that you're expressing your angles with respect to the horizontal. Because if they were expressed with respect to the vertical, you either have to compute a new angle or you got to swap your sines and cosines. Either one works. There's no you have to do it one way or have to do it the other. You just have to get the right answer. So yeah. Any questions? Okay. Let's chug on to our next example. This one's easy. This one's like, if the last problem is, well, it's not easy or hard. The last problem was a lot longer than this one, so I'll take my time on this one a bit. Okay, so a sign has a mass of 150 kilograms, and it's attached to the wall by a pin at point B, and then it's supported by a cable between points A and C, and so we have to determine the tension in the cable. Okay, before I do anything with equations of equilibrium with statics and dynamics, I want somebody to look at this problem and tell me something that they ought to do right now. There's a value that was given. Well, coordinate system, yeah, we're going to have to set that up. That's probably not a bad idea. Make the mass a force. That's exactly right. This is a mass. Weight is mass times gravity. Okay, and so whenever you're, this is another thing that I want to point out. Part of the things that I'm trying to achieve in this FE review is I want to review the concepts, but at the same time, I kind of want to review some of the things that are very easy to trip you up, and also some test-taking strategies. Like when we get to our centroids problem, there is a clear test-taking strategy that you should try and exploit with the centroids problem that I kind of want to illustrate. But one of the things, this right here, this is the type of stuff that happens on the exam, is that you're given a mass, and it's really easy to just steamroll into the statics and start breaking out your equations of equilibrium and all that stuff. And you're like, oh man, I forgot to convert it to a force. And so none of your answers match the choices, and you know, it's really easy to forget. Now remember, gravity in metric is 9.81 meters per second squared. That's a number that just should be burned into your memory. And this comes out something like 1471. Oh, 71, not 77. 1471.5. And then if I take kilograms and multiply it by meter per second squared, I get a Newton. Okay. Now, the sign, it has a weight of 1,471.5 newtons. It is supported by a cable between points A and C. Now, let's look at this cable AC. So here's the cable. Ugh, that is ugly. Let's see if I can do. Well, that's not much better. I'm going to get this. That's about the best you're going to get. Okay. Now, this is A. This is point C. This is B. This dimension here is 2.00 meters, and this dimension is 1.50 meters. I don't know about you, but if I were to, let's say, multiply both of these by 2, this would be a 3, this would be a 4. Okay, and so that's 3, 4, 5. That's a 3, 4, 5 triangle. Okay. I'm going to use that here in a second. But what I want to do is I kind of want to draw a free body diagram of this sign, and I want to use this as a means of solving the problem. Now, whenever you do this, and whenever you approach a strategy of a problem like this, always keep in mind the goal. The goal in this problem is this right here: determine the tension in the cable. So that's all I care about. And so think about summing moments, where to sum moments, all of that stuff. So let's look at the sine. Actually, let me draw this a little lower. I don't want to be squinching this. Okay. So here's my sine, okay? And I have a hinge here. Okay, and so you know that hinges have a vertical reaction, and they have, you know, some sort of, you know, vertical or horizontal reaction, although that doesn't really matter, but we can call it by bx if you'd like. Now, the centroid of that sine, it's a rectangle, so it's going to be right there. So I'm going to idealize this 1471.5 Newton force going right through here. And so that means that this dimension here is 2 meters, just like this one is, because the sine itself is 4 meters wide. And now right here, this is point C. That's point C. Okay. So I propose that point C, that's where the cable goes. That's where the cable interacts. Point C, there's a tensile force pulling at an angle right here. And so we'll call this the tension in AC. And so let's just think about this analytically. If I sum moments here, then my reactions from that pin are all going to go through the pin, so I don't have to consider the reactions. I don't have to consider the reactions, and that's going to generate just one unknown, the tension in the cable. But that tension in the cable is at a diagonal, and so maybe if I can like do this, maybe if I could do tension ACX, tension AC. Oh, that's X. That's Y. Well, that's where my 3, 4, 5 is going to come into play. So this is tension AC. And I propose then that this is tension AC X, tension AC Y. And remember that 3, 4, 5. Let's see if we can use that here in a bit. Now, the other thing to keep in mind is the principle of transmissibility. Remember, when I have, you know, some line of action and I have, you know, some vector, and I've split that vector into X and Y components, I can move those X and Y components anywhere along that line of action, okay? I can move them anywhere along that line. So I propose the easiest thing to do is to move them right here to C. If I move them to C, the X component is going to go right through. So if I sum moments at B, all right, if I sum moments at B, what do I have? I don't have to consider BX, don't have to consider BY. I do have the 1471.5 newtons at 2 meters. And that's got to be resisted by, okay, the ACX is going to go right through B, but the ACY is going to be resisting, but it's also going to be 2 meters. Well, gosh, that makes that pretty easy. I mean, a pile of junk times 2 equals a pile of junk times 2. Those two pile of junks are equal. So TACY is 1471.5. Oh, I dragged my pen. What was my pen dragging there? There we go. 1471.5 newtons. Now that's not the answer. That's the Y component of the tension in the cable. Well, how do I determine the answer? Well, I look at this, and I look at this. And remember, that's a 3, 4, 5. So I say to myself, TAC Y is to 3, as whatever the tension cable is 5. So the tension in the cable is 5/3 of the Y component, which is 5/3 of that, and that comes out to be 2452.5 newtons. And so, boom. Most nearly. I actually didn't. I should have put most nearly on this problem. I didn't. For that, yeah, that's a tad mistake on my part. Remember, the FE exam is always going to ask you, or it's very often going to ask you, what is most nearly the resultant, or what is the closest value, or what have you. All right. Any questions? I know I hopped around a little on that problem, so, oh, didn't mean to do that. I know I hopped around a bit on that problem, so I want that to be clear. Okay. All right. This one's always one that takes a little bit of figuring, a little bit of thinking. Okay. Now, let's take a look at this. So I have a coefficient of static friction. So hold on, let's go back to square one. So I have a 100-kilogram block and it's resting on an incline. First off, whenever you see 100 kilograms, recognize that this is statics. Statics is the study of forces. So you're going to need to convert that to a force. So, force equals mass, or weight equals mass times gravity. But we'll handle that here in a second. The coefficient of static friction between the block and the ramp is 0.2. The mass of the cable is negligible. The pulley is frictionless, so that's not a big deal. What is the smallest mass of block B that will start the 100-kilogram block moving up the incline? Okay, so let's take this one step at a time. Okay, so first thing we're going to need to do is we're going to need to draw a free body diagram of this, and we got to get pretty detailed in our free body diagram. Okay, so let's handle that. So here's our slope, and we have our box right here. So this is box A. Okay. Now, whenever we're handling things lines and we're summing forces, especially with friction, we kind of need to define a coordinate system. And so typically what I'll do is I'll say that this is the y-axis and this is the x-axis. The reason why I do that with friction problems is because friction, remember, what's our standard formula for a frictional force, right? It's a normal force times a coefficient of static friction. And so the normal force is going to go along the y-axis, and the normal force is going to go along the y-axis, and the frictional force is going to go along the x-axis because it's perpendicular to that. That's kind of why I draw my coordinate system like this. Okay, so that's my block A. Now, this is a block and it has a mass. Okay, so the first thing we have to do is we have to draw our weight of this block, and weight is always going downward every time. Okay, so this is going to be our weight. Okay, weight is mass times gravity, and mass is 100 kilograms. And 81 newtons. Okay. All right. And so what I'm now going to do is I'm going to take this W sub A, and I'm going to see if I can split it up into an X and Y component, if you will. So we'll say, maybe we'll do this, Fx A and Fy A. Okay, so Fxa and Fya. All right, so we're going to take the weight multiplied by something. Okay, so here's this. Okay, now this slope ratio, this is 30/40. So this is again another 3/4 slope ratio, which by the way, 3/4 slope ratio is pretty common on this section of the exam because it's a 3, 4, 5. 5, 12, and 13, that's another common one. I think it's 7, 24, and 25, 8, 15, 17. Those are all pretty common instances of slope ratios you see on the exam. And then there's also some simple ones like 1-to-1 and what have you. Okay. Now, this box is, it's on a slope. The slope ratio along the x-axis, the index, it is bigger, right? Which means that the box is lying more flat than it is vertical, okay? So if the box is lying more flat than it's lying vertical, what that means is that the vertical component has got to be the bigger value, right? I mean, if I have my coffee cup sitting here on this table, the table's completely flat, so if I split the weight up into X and Y, the Y is going to be the biggest. And if I only tilted it up slightly, yeah, I'm going to get a little bit of X component, but the Y component is going to be much bigger. The X component doesn't get bigger until it gets really, really high up. So this one is going to be the 3/5. This is going to be the 4/5. If that's a little hard to follow, just remember this from strylysis when we did inclined rollers. When you have a slope ratio, but you want to determine the X and Y component, you flip them. So that's kind of what we're doing here. Now, this term times 3/5 is 588.6. This one is 784.8. Okay, so this box has a horizontal component wanting to push it down the hill, and it has a vertical component acting into the ramp. Now the ramp responds by developing a normal force equal and opposite of that. So the normal force is equal to the Fya, which is 784.8 newtons. Okay, so it's like my coffee cup. My coffee cup, if it weighs like 1 pound and it's pushing down on the table responds with a normal force. 1 pound's going up. So that's our normal force. Now, we can go ahead and compute our frictional force. So that's mu sub s Fn, or 0.2 times 784.8. Which is, what is that? 156.96. That's the force developed by friction, right? You're in your house and you're pushing your couch or your refrigerator across the floor, that it responds with a frictional force in the opposite direction. The big question to ask is, which direction does the force act? And the best way of answering that is to try and determine what we're trying to do with this block. Okay, so let's go back to the problem. The problem states that we've got this block, and Sorry about that. We've got this. What's going on here? Why is it doing that? Apologies. Okay. So we've got this block on an incline, and we're trying to determine how much force is required to start moving the block up the incline. So there's this force going this way, which is actually going to be the weight of that block. And so we're pulling the block up the incline. And so if we're trying to pull the block up the incline, the frictional force is going to act in the opposite direction. It's going to act to resist that motion. Okay, so that's kind of important in terms of the direction. So now what we can do is we've completely defined all of the forces on the system. Now what we have to do is we have to sum forces, in this case in the x direction, to determine what's going on here. So I've got, I'm using my coordinate system that I've drawn right here. So Fxa is going on the left. The frictional force is acting left, and the weight of that block is acting to the right. So it's an F. Fxa. So that is 156.96 newtons plus 588.6 newtons, which is 745.56 newtons. So I propose that if I want to get that block to start moving up the hill, I've got to have a force that's at least 745.56 newtons or bigger, okay? But is that one of my answers? Well, no, because the problem is asking for the mass. It's asking for what is the mass of this block that will push this up the hill. Because keep in mind, we've got this pulley, and we've got a rope here, and a rope here. So this is, 745.56 newtons. So, that mass has to pull it down 745.56 newtons. The question is, what's its mass? Well, it's simple. If I know its weight, the mass is the weight divided by gravity. And so take that, divide it by 9.81, you get 76 kilograms. That's a little bit of an involved problem on the exam, I know, but help me out. Any questions on this? Any doubts? Anything that we can elaborate on? Okay. Last one, and this last one I want to do is kind of important because this illustrates not just, in my opinion, a very simple calculation. One of the things that I want to try and illustrate on the FE exam is that, in my opinion, there are certain problems that are free throws, that are just, gimme shots, just go for it. And one of them is determining the centroid of an area, because remember your expression for computing a centroid. So, x bar is the sum of ax over the sum of a, and y bar is the sum of ay over the sum of a. Those are pretty typical problems in the world, or pretty typical formulas in the world of statics, and these are very, very doable questions. So the first point I want to get across is this is very plug and chug, and so you should go for it if you see this. Don't, oh, I don't know, like, oh no, this is doable. But here's the other thing. I want to talk about this from a test-taking strategy. I want to get your feedback on this. I want you to look at these choices and tell me about if anybody recognizes a test-taking strategy that we can employ on this problem. Keep in mind, the problem is asking for what are the X and Y coordinates of the area of the centroid. I'll move this down. Anybody notice like a test-taking strategy? Let me ask it this way. C cannot be D. That's one very good observation that actually wasn't what I was talking about, but that's actually pretty good. What Mr. Stratton is saying is that because of the geometry, it can't be D. And he's right, because D would be the centroid of just the rectangle, right? But there's holes in it, so it can't be D. Okay, that's actually a really good point. So yeah, I'm gonna go along with that. But there's something else. Let me guide it. Let me sort of go about along with this. In order to determine the centroid, we need a point, x comma y, x bar comma y bar. Okay, but here's the thing: none of these x bars match. None of them are common. None of these are common. So from a test-taking strategy perspective, why do both? Why not just do the x bar? Because if I do the x bar, I don't need to do the y bar. I'm going to get the answer, because it'd be different if like this was 3.4 and this was also 3.4. So if I did x bar and I got 3.4, well, I know it can't be C, but that doesn't tell me the final answer. I have to go through and do more work. But because they're all unique, just do one of them. Okay. Now, what I'm going to do is I'm going to split this up into 3 regions. We're going to have the rectangle, the square hole, and then the circular hole. Now, the area of that circular hole is pi over 4 d squared, which is pi over 4 times, what is that? It's a 4 centimeter diameter, so 4 centimeters squared, and so that's 12.57 centimeters squared. Okay, so let's go ahead and do that. And remember, the easiest way to do a centroid problem is to set this up as a table. So we have the shape, we have A. Here, let me drag this down a bit. I'll redo this. The shape, the area, and then we can do either X bar or Y bar. It doesn't matter. I'm just going to flip a coin and do X bar, and then AX cubic centimeters. Okay. So there's 3 shapes. Okay. So I propose that we'll do just the rectangular plate. Let's do the square hole. And let's do the circular hole. All right. And so what are the areas of each of these shapes? Well, the area of the rectangular plate, it's 8 centimeters wide, and it's 8 centimeters wide. It's 10 centimeters tall. So that's going to be 80. The square hole. Now, the square hole is 2 by 2. So the area is 4, but that's a hole. So the area is negative because we're taking material out of the plate. And same thing with the area of the circular hole. We got 12.57, but that area is negative because we're taking material out of the plate. So if I sum up the areas, that's going to be 80 minus 4 minus 12.57, so that's 63.43. Now the X bar. Now what we do is we pick a common axis, which we don't have to do that here because we know where the coordinate system is. The coordinate system is right here. That's the origin. It was already told to us. And so the question is, how far is it from the x-axis, or how far is it from the origin? So there's the origin right there to the centroid of each of the simple shapes. So for the big rectangular plate, that's going to be 4, okay, because we're talking about, you know, like this point right here, okay, and so that dimension there is 4. And so how far is it for the square hole? Well, it's going to be 2, because there's the centroid of the square hole, and so we go 1 centimeter to the edge, another centimeter to the center, and so that's 2. And as for the circular hole, well, that was actually told. That was given to us right here, and that's 5. And so now you just do a little bit of multiplication. 80 times 4, 320. 4 times 2, that's 8, but that's negative. And then 12.57 times 5, that comes out to 62.83, and that's negative. And so sum these up, and you get 214.17. And so therefore, x bar is the sum of ax over the sum of a. So that's 240, not, I can do better than that. 249.17 cubic centimeters over 63.43 centimeters. That's square centimeters. And so when you divide that out, you get 3.93 centimeters. And so here's the thing. That's the x coordinate. So if you go up here, I haven't even done the y coordinate, and I can tell you that the answer is C. All right, I can tell you the answer C, because if I got the x one to match, well, it's not B, it's not A, and it's not D. Even if we hadn't observed what Mr. Stratton had, that you know, it can't be D because of the presence of the holes, it's still like you only have to do one. So again, I wanted to review the topic today, but I also wanted to review some common test-taking strategies that can help you out, and also some of the things that you could get caught up on. Now, I haven't uploaded the quiz yet. That's probably going to be a little bit later this afternoon. I actually have statics here in about 10 minutes, so I will. I'll do that probably before I leave today, and that'll close next Wednesday. In the meantime, I am probably going to send a message on Teams about you know, what topics to move forward. I mean, let me know. Put some stuff in Teams, chat it out, have some discussion. There's nothing wrong with that. Just like what happened this week, like don't say nothing, like say something. So, but yeah, anybody have any quick questions before we call it? All right. Well, that's all I have. I'm going to hop on over to statics and talk about moments about axes. So that's all I have. I'll put some posts in Teams to let you know when the quizzes are up, and that's all I have. I will see you all next week.